Welcome to Lesson 3 of Module 1, where we will discuss some examples of ML applications and why they are successful. Today's activities will introduce some of the most common ways that machine learning is used, along with examples of successful applications that leverage these techniques. In this lesson, you will learn about common types of problems that you might encounter and which lend themselves for using ML. You will review examples of the problems and see how AWS customers have used AWS to support their ML solutions to problems. First, consider regression. Imagine that you are a real estate agent and you want to predict the sale price of a house based on its characteristics, such as size, number of bedrooms, number of bathrooms, age, and location. You have a dataset that contains the sale price and characteristics of houses that have recently sold. You can use this dataset to build an ML model that can predict the sale price of a house based on its characteristics. This is a regression problem because the output, predicted sale price, is a continuous numerical value. To build the model, you would first split the dataset into a training set and a test set. The training set is used to fit the model, and the test set is used to evaluate the model's performance. You would then select an appropriate ML algorithm, such as linear regression or a decision tree, and use the training set to train the model. After the model is trained, you can use it to make predictions on the test set and compare the predicted sale price to the actual sale price to evaluate the model's performance. This is only one example of an ML regression problem. However, regression can be used to predict a wide range of continuous numerical values, such as stock price, temperature, or blood pressure. A fantastic example is the NFL's Next-Gen Stats page, powered by AWS AI. This is an ML-powered solution that takes data like weather, opponent strength, historical data, and other information related to the game. This algorithm then uses this data and apply linear regression for player statistics and performance prediction. Classification is another type of the most commonly encountered types of ML problems. In this example, the problem is to classify whether a learner or student of a course will get a word correct from the given language depending on various characteristics of the learner. The input features may include the learner's age, proficiency level in the language, completion percentage for the course and lesson, and number of times the learner has encountered the word before. The output is whether the learner will get the word correct, yes or no. In this classification problem, the input features are various characteristics of the learner and the word that they are trying to learn. The output is a binary classification of whether the learner will get the word correct. To solve this problem, you would need to train an ML model on a labeled dataset where the input features and the output label, whether the learner got the word correct, are known. You could then use this trained model to predict whether a learner will get a new word correct, given their characteristics and the characteristics of the word. Several models could help you solve this example problem, including the following: logistic regression. This is a simple and effective model that is often used for binary classification problems. It works by fitting a line or curve to the data, and using it to predict the probability that an instance belongs to a certain class. Decision tree. This is a tree-like model that makes decisions based on the values of the input features. It splits the data into smaller and smaller subsets that are based on the values of the features until it reaches a final decision about the class of the instance. Random forest. This is an ensemble model that consists of many decision trees. It works by training multiple decision trees on different subsets of the data and then averaging their predictions to make a final prediction. This can often improve the accuracy of the model. Support vector machine, SVM. This is a powerful model that works by finding a hyperplane in the feature space that maximally separates the different classes. It is particularly effective for highly dimensional datasets. Neural network. This is a complex model that is made of layers of interconnected nodes and is inspired by the structure and function of the brain. This model can be effective for a wide range of classification problems, but can also be more difficult to train and can require more data. Ultimately, the choice of which model to use will depend on the specific characteristics of your dataset and the requirements of your problem. It might be necessary to try different models and compare their performance to find the best one for your needs. This holds for all the examples I will be presenting. Typically, classification problems have requirements such as identifying whether an image contains a delivery box or classifying text as having positive or negative sentiment. However, with a little creativity, these problems can span a much greater range of applications. Consider this case study of Duolingo applying a classification problem to language learning. For every word that you learn, Duolingo tracks information such as how often you've seen it, how often you've identified it correctly, what context you've seen the word in, and how long it has been since you last saw it. To ensure that the user is presented with the correct word at the correct time, the company uses ML to predict the probability that a user will correctly identify a word so they can surface those words that are most in need of review. For more information, see AI helps Duolingo personalize language learning at https://aws.amazon.com/machine-learning/customers/innovators/Duolingo. Next is an example of ranking, which is the problem of ordering a collection of results. In this example, the problem is to rank a customer's most likely next pizza order. The input features could include the customer's past pizza order, their location, the time of day, the day of the week, the current weather, and special promotions or discounts. The output is a ranked list of the most likely next pizza orders for the customer. In this ranking problem, the input features are various characteristics of the customer and the current context. The output is a ranked list of the most likely next pizza orders for the customer. To solve this problem, you would need to train an ML model on a dataset where the input features and the desired output, the customer's past pizza orders, are known. You could then use this trained model to predict the most likely next pizza orders for a customer, given their characteristics and the current context. Several models could help you solve this example problem, including the following: collaborative filtering. This is a type of model that makes recommendations based on the past behavior of similar users. It works by identifying users with similar tastes and using their past actions to predict the preferences of a new user. This approach can be effective for ranking problems because it can take into account the complex relationships between different items and users. Pointwise model. This type of model directly predicts the likelihood of each possible item being chosen. This model can be used to rank items based on their predicted scores. You can train a pointwise model by using techniques such as matrix factorization or deep learning. Pairwise model. This model predicts the relative order of pairs of items. This type of model can be used to rank items by comparing their predicted scores to each other. You can train a pairwise model by using techniques such as support vector machines, SVMs, or deep learning. Again, the choice of which model to use will depend on the specific characteristics of your dataset and the requirements of your problem. The most common application of ranking is a list of search results. Consider the case of Amazon Personalize, which helps elevate customer experience with AI-powered personalization. It can be used, for example, to hyper-personalize and rank streaming recommendations by personalizing and ranking movie, TV, and music recommendations, tailored to what customers are most likely to be interested in watching. Or to deliver popular and seasonally relevant travel content across channels, by ranking hotel and flight recommendations to highlight popular products, seasonal merchandise, and time-bound promotional offers. Recommendation is one of the primary use cases of ML across many companies. This is the ability to use past behavior to recommend content or items that a user might like, for example, recommending products on an online store or posts in a social media app. These techniques can be integrated into almost any business. In this example, the problem is to recommend hotels for large events. The input includes the location of the event, size of the event, number of attendees, desired price range of the hotels, desired rating of the hotels, and desired amenities of the hotels, such as a swimming pool or conference rooms. The output is a ranked list of recommended hotels for the event. In this recommendation problem, the input features are various characteristics of the event and the desired characteristics of the hotels. The output is a ranked list of recommended hotels for the event. To solve this problem, you would need to train an ML model on a dataset where the input features and the desired output, the characteristics of the recommended hotels, are known. You could then use this trained model to recommend hotels for a new event, given the characteristics of the event and the desired characteristics of the hotels. There are several models that you could use to solve this recommendation problem. Some options include collaborative filtering. This is a type of model that makes recommendations based on the past behavior of similar users. It works by identifying users with similar tastes and using their past actions to predict the preferences of a new user. This approach can be effective for ranking problems because it can take into account the complex relationships between different items and users. Matrix factorization. This is a type of model that decomposes the user-item interaction matrix into a low-dimensional latent feature space. The model can then use these features to make recommendations by finding the items that are most similar to the ones a user has liked in the past. Matrix factorization can be trained by using techniques such as singular value decomposition or alternating least squares. Deep learning. This complex model is made up of layers of interconnected nodes and is inspired by the structure and function of the brain. This model can be effective for a wide range of recommendation problems, but can also be more difficult to train and can require more data. Deep learning models can be trained by using techniques such as autoencoders or neural collaborative filtering. Recommendation techniques can be integrated into almost any business. For instance, Hyatt Hotels uses a recommendation system to recommend hotel choices for large events, such as conferences, for repeat customers based on the preferences that they've expressed in hotels that they've used in the past. For more information, see Hyatt Hotels enhances personalization on AWS at https://aws.amazon.com/solutions/case-studies/Hyatt Hotels case study. Clustering is an unsupervised learning technique that attempts to find groups or clusters of similar items, given a collection of examples. Clustering is often used for tasks such as grouping similar behaving segments of customers or products. In this example, the problem is to create an automated image tagging system. The input includes collection of images and pixel data for each image. The output is a set of tags or categories for each image. In this clustering problem, the input is a collection of images and the pixel data for each image. The output is a set of tags or categories for each image. To solve this problem, you would need to train an ML model on a dataset where the input images and their corresponding tags are known. You could then use this trained model to predict the tags for a new collection of images. One approach to solve this problem is a clustering algorithm, such as k-means or hierarchical clustering. These algorithms work by grouping the images into clusters based on their similarity to one another. You can then use the resulting clusters to assign tags to the images. Alternatively, you could use a deep learning model, such as a convolutional neural network, CNN, to automatically extract features from the images and use these features to classify the images into different categories. Several models could help you solve this example problem, including the following. Clustering algorithm. This algorithm groups data into clusters based on their similarity to one another. Some popular clustering algorithms include k-means and hierarchical clustering. Clustering algorithms can be effective for image tagging problems because they can group similar images together and assign them common tags. Deep learning. This complex model is made up of layers of interconnected nodes and is inspired by the structure and function of the brain. This model can be effective for a wide range of image classification and tagging problems, but can also be more difficult to train and can require more data. Some popular deep learning models for image classification include CNNs and transfer learning models. Disney is building an automated tagging system that tags all content that is stored in the Disney catalog with what characters are present, the topic, and the scene. This information will help animators and writers to quickly search the catalog to answer questions such as how often a particular droid appears in episodes of a show. New images can be added to an existing collection at any time, and these will be processed on arrival and added into the clustering results. Likewise, updates to the data will automatically invoke the data clustering algorithm. The creation of the complete metadata is a collaboration between ML-powered systems that identify relevant clusters of faces and other objects, which are then annotated by a human annotator. For more information, see with deep learning, Disney sorts through a universe of content at https://aws.amazon.com/machine learning/customers/innovators/Disney. Finally, anomaly detection attempts to detect outliers or unusual patterns of behavior from a dataset of examples. In this example, the problem is to identify novel fraudulent behavior. The inputs include historical data for fraudulent behavior and current data on suspicious activities. The output is a prediction of whether the current activity is likely to be fraudulent. In this anomaly detection problem, The input is historical data for fraudulent behavior and current data on suspicious activities. The output is a prediction of whether the current activity is likely to be fraudulent. To solve this problem, you would need to train an ML model on a dataset where the input features and the output label, whether the activity is fraudulent, are known. You could then use this trained model to predict whether new activity is likely to be fraudulent. Models could help you solve this example problem, including the following: density-based anomaly detection. This type of model identifies instances that are significantly different from the majority of the data. The model works by estimating the density of the data and identifying instances that have a low density compared to the rest of the data. Some popular density-based anomaly detection algorithms include local outlier factor, LOF, and one-class SVMs. Model-based anomaly detection. This type of model uses a probabilistic model to fit the data and then identifies instances that are unlikely according to the model. This model can be effective for anomaly detection problems because it can consider complex relationships between the different features in the data. Some popular model-based anomaly detection algorithms include Gaussian mixture models, GMMs, and autoencoders. Deep learning. This complex model is made up of layers of interconnected nodes and is inspired by the structure and function of the brain. This model can be effective for a wide range of anomaly detection problems, but can also be more difficult to train and can require more data. Some popular deep learning models for anomaly detection include variational autoencoders, VAEs, and generative adversarial networks, GANs. Anomaly detection is especially important in industries like finance, retail, and cybersecurity, but every business should consider an anomaly detection solution. It provides an automated means of detecting harmful outliers and protects your data. For example, banking is an industry that benefits from anomaly detection. Using it, banks can identify fraudulent activity and inconsistent patterns and protect data. Predictability is the next step for anomaly detection. With predictability, you can find outliers on a machine level. Finding them helps prevent harm to your system before they occur. For example, a hospital that doesn't know what an attack will look like can benefit from predictability. With predictability, the hospital can write rules to prevent the attack, protect sensitive data, and their environment. For more information, see this AWS anomaly detection at https://aws.amazon.com/what/anomaly detection/. In the next lesson, we will cover overfitting and underfitting, as well as the ML lifecycle. Thank you for watching this video, where we provided examples of various ML applications of AWS customers and illuminated why they are successful.